So I think we can start. So on Monday, we started discussing about surrogate-based approaches, but we did not do much really. We just talked about the philosophy of surrogate-based models. We talked about the important components of surrogate-based models, and we talked about how it can potentially be a balance between non-sampling based approaches and sampling based approaches. And more or less, this is what we discussed on surrogate based approaches last Monday. So today, let me start with the most basic surrogate based model or surrogate based approach. In fact, this is the perhaps also the most widely used surrogate based approach, because this was the first one people were using it, and it is only a recent phenomena that people have moved towards advanced surrogate based models, surrogate models such as Gaussian process, polynomial chaos expansion, and so on and so forth. So today, as I was saying, right, we will talk about one of the surrogate based model, which is the simplest one, and this is basically the response surface method, right? But before that, let me start with a quick recap of what we are looking at in reliability analysis, and a quick recap of what the objective of surrogate modeling actually is. So let us start with that, right? So if you remember, in reliability analysis, we have random variables, the inputs are random, and that's why we are interested in reliability analysis, which fundamentally means computing the probability of failures, right? And I'm using the term probability of failures because in a generic sense there can be multiple system, or a single system can have multiple components, and each of the component can have its own failure probability. And by combining them, the system can have its own failure chances, right? So generally, in reliability analysis, we are interested in computing the probability of failure. The objective is to compute the probability of failure, right? But to compute probability of failure, we have defined certain things. So first of the thing is, let's say x, and x denotes my input random variable. Input random variable, and then you might have multiple of these variables. So therefore x is generally x1, x2, and you might have k such variables. So x is generally a k dimensional vector, given that, I mean, that, so your input can be a k dimensional vector, right? And when we write something in subscript, this means the first random variable, right? Given that I have some data, I also denote x as, so if x is the data matrix, let's say, so x sometime is also written as x1, x2, x t, let's call it, okay? So when you see something like this, generally it will represent samples. This is samples of x. This is like the first sample, and then you have, in this case at least, t such, nt such samples, right? We also define a function, limit state function, which defines the boundary between the failure and the safe zone, and limit state function we generally define as g of x equal to 0. So, this generally denote my limit state. We also define failure domain, which is all those x corresponding to which gx is less than or less than equal to 0, and this denotes my failure domain. And given that all of these are defined in reliability analysis, you compute the probability of failure by solving a multivariate integral, a high dimensional integration problem. So, given all of this is defined, your probability of failure is integration over the failure domain of the PDF of the random variable, and this is a multivariate integral. I mean, in this case it is a k-variate integral based on the notation. Correct. So, x is a random variable. So, the first one is denoting that in sometimes we will denote x1, x2, where like x1 is the first random variable, x2 is the second random variable, and sometime x we will write it x1, x2, x3. In that case, x is the collection of samples drawn from the random variable, and in that case x1 will denote my first sample, second sample, and kth sample. So, correct. Okay. So, in that case, so when I am writing x1, it means it's a k-variate or k-dimensional first sample. So, in that sense, right? So, obviously I am writing here. If I was typing it, the first x would be bold and italics. The second x would be only bold. If I was typing it, it would look like that. The first x left hand side should be bold and italics. The second x would be only bold. Bold means matrix, bold and italics means vector. So, in that notice, right? Okay. And now we also know that we have already discussed this is equal to indicator function gx less than 0 fxx dx, which now you can, using the law of large number, you can approximate it as 1 by n summation over I equal to 1 to n I g of x I less than 0, where xi is a sample drawn from the PDF fxx, right? All of this we have discussed. This is nothing new. I am just reviewing it for two reasons. One is the exam is near. The second is I am reviewing it to give you a recap, so that when I go into response surface method things, some of the things are fresh in your mind. So these are the two reasons I am doing that, right? This is fine, right? We have all discussed it. Now, in surrogate based approach, our primary objective, as discussed in the last lecture, is to approximate this g or replace this g with an easy to evaluate function g hat x. That is the objective of surrogate model, right? So, in surrogate based approach, gx is replaced by g hat x, where g hat x is now known as my surrogate model. This is my surrogate model, right? And with this background, we are now going to talk about, in today's lecture, about one of the surrogate models, which is the response surface method. Okay. So, we will discuss response surface method. Okay. This is what we will discuss today. Now in response surface method, what is response surface method? Originally when the term response surface method was proposed, it essentially meant polynomial regression. So originally, if you look into history, when the response surface method was proposed, it meant polynomial regression. Okay. But then as the literature evolved, people started using response surface method, and rightly so, as a synonym to surrogate model. Because its response surface method is what? A function that approximates or represents the limit state surface. Now I call it limit state function. You can also think of it as limit state surface, because it's not a line, it's a surface kind of thing that it gives, right? And response surface is something that approximates that. So originally it was polynomial regression, but later it is used today as a synonym to surrogate model. So I talked about synonyms in the last lecture: surrogate model, meta model, emulator, response surface method. This is another one. Okay. So this was originally polynomial regression. But now used as a synonym to surrogate model. Okay. Now in this course we will use it. We'll go by the first one. When I say response surface method in this course, I refer to polynomial regression only. By response surface, I do not refer to, let's say, a Kriging or a Gaussian process or a neural network. I do not refer to it like that. But in literature, it is referred like that also. So for the sake of this course, when I say response surface method, I will refer to polynomial regression. Okay. So this distinction I wanted to make, because you will read paper and you might get confused. Because in paper it is often, nowadays at least, the second one. Although even that is stopping now. But for this course we are going by the original definition, the original how it was proposed. Okay. So fundamentally we are going to talk about response surface method, which means we are going to talk about polynomial regression. That's all. Okay. Response surface method, response surface model is also what it is called. So remind me, what is the objective in surrogate modeling? G hat of H we want to learn, right? And what is response surface method that I just defined? Polynomial regression. So what do you think I'm going to do? Use polynomial regression to approximate the G of X, or rather use polynomial regression to find or represent G hat X. As simple as that. That is all what I'm going to do, right? So response surface method, right? So you have X, which is your input variable. Okay. What you do is that you sample this in surrogate model. What is the first step? Last time we discussed steps. What was the first step? To generate sample, design of experiments, right? That is the first step. So even for response surface method, the first step will be to generate training samples, to generate samples. So let's assume that we have used some design of experiment, because I have not yet discussed design of experiment. So let's say we have used some design of experiment, and using the design of experiments, I have samples for this random variables. Okay. That is the consideration that we will proceed with. So we have generated X. So let's use this notation, but it's a matrix now. Okay, using some design of experiment scheme. Okay, what DOE I have used, I am not specifying. It can be a Latin hypercube sampling, it can be a Sobol sequence, it can be a central composite design, factorial design, and all of this we'll talk about later. But we have this samples available to us. So how will X look like? This X will be a matrix. How will it look like? I have how many variables? Notation tells K. For each variables I have generated samples, right? So the row generally denote, each row is one sample. Each column is one variable. So the first one will be x1 1, x2 1, and you have xk nt, right? Training sample, number of training sample, that's why. The next will be x1 2 1 1, correct, thank you, correct. One x1 2 x2 2 xk 2, and then x1, now it should be nt, x2 nt, xk nt. This is how your input samples, training sample, if I write it in form of a matrix, this is how it will look like. Okay. And what is the dimension? The dimension is nt rows cross k, right? So this is the sample that I have generated by using some design of experiment scheme. I am not specifying whether X, the vectors are dependent, independent, I am not specifying that. I am not specifying what design of experiment scheme I have used, but this is what I have now. How will I reach this point is something we will discuss later. Okay. What is step 2 in surrogate modeling? Generating the output. So we will use the limit state function and evaluate the limit state function for each of these rows. Each row is a sample. So for each of the rows you will evaluate the limit state function, and that will give you the output. Okay. So we also have y in that case, and y is a vector where for each row I will get a single value of y. So the first row will give me g evaluated at x for the first sample, right? The second one will be, and like that I am not writing, I am just writing the last one, g for x evaluated for the last sample. Okay. This is what I will have, and this dimension is r cross, r nt, and I will call it, I don't want to write this g of x1, g of x2, I will call it y1, y2, ynt, right? I will call it y1, y2, ynt, but y1 is nothing but g evaluated at the first sample. Keep that in mind. Okay. So this is what is given to us. Now what do I want to do? My objective is to learn a mapping from x to y, and that mapping should represent Gx as closely as possible. So in response surface method, so in RSM, we consider, or rather we model y to be approximately equal to, because it will not be exact, W naught plus summation I equal to 1 to NB Wi psi I of x. This is a linear regression model, right? This is, everything is linear in W's, so that's why it's a linear regression model. Where W is my, what do we call it? Weight. What is W naught? Bias. What is psi? Basis function. Polynomial basis in this case, but in general it is a basis function. It will become polynomial when you do a response surface, but because we are talking in a generic sense, it's a basis function. It can be any basis, right? So this is how you represent it, and this basis function can be non-linear, by the way. Because I am saying it is linear regression does not mean that the basis function will be linear. Linear regression it is called because it is linear in weights, not linear in x. So that is one small distinction that should be clear to you, right? Okay, I mean, if I want, I can write it in this form also. W transpose psi x. If I want, I can write it in the vectorized notation. Clear? Now, to distinguish this from this, I am going to put a line below, because that's like a vector. This y is not a vector. This is for a given x. This is the functional relation. Y is the output of a function. It will become vector if I evaluate it at different x and stack it. Otherwise, this y is just a response. That's just the output. So it's not a vector to start with. Okay. This is fine. What is known to us? What is unknown in this? Psi is known. I will select it. Basis function. The W's will be unknown. The weights and biases are the unknowns. And weights and biases are something that I will like to estimate based on the training data, this data that I have generated using design of experiments. So the objective with this become, so the objective is find, okay, W is a vector, right? Find W using x and y, right? This is my simple objective. How will we find it out? It's a regression problem, and we know that we want our g hat x. This is my g hat x, by the way, this equation. We want our g hat x to be as close as possible to gx as possible, which means I will want the output of the right hand side, which is my g hat x, to match to this y as closely as possible, which means I will define some statistical quantity which gives me the difference between the gx that I got by running the simulator, the y that I get by running the simulator, and y hat or y tilde, whatever you call it, that you get from this model. And you will try to minimize that statistical quantity which measures the difference, and you will try to push it towards as low as possible. Ideally 0, which will not happen, but ideally we are interested in learning the function, by the way, right? That is the goal. Machine learning, I will define this quantity is known as, in machine learning we call it loss function. So we will define a loss function, right? And the most popular common loss function is squared error, right? I don't even need to do mean because 1 by n is redundant. It will be a squared error. Objective, okay. So for that, we define, or rather we use, I should say, we use squared loss, right? And if I use squared loss, my loss function will be L is equal to summation J is equal to 1 to NT. These are the number of samples I have. For each of the samples, I will have G of x1, G of x2, something like that, which I will call as Y. So Yj, the original one. Yj, the jth sample, minus whatever I can predict, which is the top equation, with x being substituted as xj. So minus W naught minus summation J I have used, so I will use 1 to NB Wi psi I x j, and that is squared, so a square of that, right? This is my loss function. And from this loss function, I want to find out W naught and W what I, where I goes from 1 to NB, right? How do you find out from loss? You want to minimize, so you will take derivative with respect to the unknowns. The unknowns are weights and biases. So let us take derivative. Let's call it equation 1. So you can also use decide. So absolute loss, which is L1 loss. L1 loss generally gives you sparsity. So you use L1 loss when you know that some of the terms can go to 0. Some of the weights can go to 0. If you want to induce sparsity, you can either do L1 regularization or you can use L1 loss. But L1 loss, remember, is not differentiable at 0. So that's why it is not preferred, whereas this one is differentiable. Relative also can be used. It depends. So relative you will use when this y is right. They are, let's say, quite far apart. So one is 1000, one, let's say one is 1 y, the other one is, other y is 1000. So if you use this, instead of 1 you get 2. So 2 minus 1 square is 1. 1000, 1 minus 1000 square is also 1. But you know that getting 2 instead of 1 is a 100% error. Getting 1001 instead of 1000 is fine. So when this kind of data is there, then you should normalize it. Okay. So all of that can be used, but it's a problem specific choice. But in response surface, generally L square is O, because remember polynomial regression we are talking about. So long back this was proposed. So okay. So differentiating, obviously L2 is also not perfect. It has its own limitations. It is very sensitive to outliers. So if there are outliers, this is a very bad loss function and all those things, right? But in this case, we do not worry. Can you tell me why? We worry about these things mostly in machine learning, but in reliability, we will not worry about this. No, let him answer. Then I will. Do not answer two people together. Yeah. No. Why? Y is not from PDF. X is from PDF, but X may not be from PDF. I'm sampling X. You were saying something? No, that has nothing to do with it. Any idea why? Will we have outlier in this case? Outlier when do we have? When there is some issue with data collection, when there is some data is highly noisy and all those things. In our case, in reliability, where is data coming from? By running the simulator, we want to match the simulator. If the simulator is wrong, we want to match that simulator. I'm not even claiming I want to match the reality. And because the data is getting generated from simulator and you were generating it, there is no noise and there is unlikely there will be any outlier. Outliers happen, let's say you are taking a record, right? And instead of a point up next, it went to the next point. So it becomes 10 times. Instead of 1.1, you wrote 11. Or you wrote 1.1, but the one who is reading, you could not detect your point and read it at 11. So that's an outlier, right? So
we are not going to use this for any level of experimental problem, this reliability.
You cannot use it. It's not that you are not going to use it, you cannot use it. Let me put it that way in most cases. Why? Because for reliability, we are looking at to evaluate the function again and again. So you have to do it experimentally. You have to perform experiments, and based on that experiment, you will go to the computer, it will update, and then it will tell, okay, now I perform experiment at this point. And this will continue 1,000 times. So 1,000 experiments. Not possible, you can understand, right? There are experimental reliability. You can compute reliability of the experimental process. You can also evaluate reliability when there is a random vibration. The force is a white noise. So all of that is possible, but mostly you will see, I mean, almost 0% of times.
Reliability we just model that thing into a simulator and then
not model that. When do you compute reliability is the actual question. Why are we computing reliability? I think that is the most fundamental question. Because we want to make our system reliable. And how will we make our system reliable? Mostly in at the time of design. So when I'm designing it, the system does not exist. It only exists in my computer. So what experiments are we talking about for that system? You will perform experiment, by the way. It is not free of experiment. You will perform experiment to find out the PDF of the random variables. So if you are building a bridge, it will be made of steel. So those steel samples will take to lab, perform experiments, and based on that characterize the PDF of the steel, the property, let's say. So nothing is free of experiment, obviously, but at what stage the experiment is, that you need to see. But the whole building, you cannot do experiment, right? Yes, in reliability experiment comes when you are trying to find reliability or remaining useful life is a more appropriate term of an existing building. In that case, the building exists. You don't know the physics because let's say it's a heritage building, over years there has been deterioration and you don't know the properties. In that case, you will go and collect some data based on, and those are experimental data now, real world data, not even experiments. Based on that data, you will solve an inverse problem to find the physics. And based on that, you will now try to find out the degradation law. And from there, you will try to find out the remaining useful life. But most of the time, reliability is done during the design phase when the system does not exist. So experiment is of a building at least is out of the picture. Okay.
And we're not concerned about the outlines where we are feeding the same eggs to the actual limited company parameters.
I am saying that outliers can come because of different reasons. One of the primary reasons is measurement error. As I said, you took some note, 1.1 became 11. That is one of the ways outlier can come, right? In this case, you are getting data from simulation. So you are not taking reading, those kind of human error and all those things are out of the picture, right? So that's why. You are doing everything in a controlled setup. I mean, if I have to say in one sentence. So because it is controlled simulation setup, right? Okay, so differentiating L with respect to W, what are the notations I have used? J and I, K. What will I get? Will be equal to, derivative will go inside the summation, the square will come outside, so it will, so it will become 2. So summation J 2 times Yj minus W naught minus summation over I Wi psi I of x j multiplied by minus of psi k, because I am taking with respect to wk. So because inside there will be a term wk psi k, you take derivative with respect to wk, you end up with psi k and a negative sign. So multiplied by minus psi k. X j, and this is also, I mean, this would be inside the summation only, right? I mean this summation, this is all, I mean, there should be a bracket here because it is for each data point you will get, I mean, that will be repeated multiple times. You will end up getting it for different. How many such W's will you have, or what will be the range of this k? K will vary from 1. The way I have written it is from 1 because bias I am taking separately. So 1 to NB. So k goes from 1 to NB. And you can also take with respect to bias, that will, the outside term will not be there, the rest will be same. There will be a negative time term coming, which I am not writing. Minus W naught minus summation over I Wi psi I x j. This was square, and then there should be a minus 1 because of the, so I can write a minus here, but that minus will anyways not matter. And this will give you one more equation, correct? How many equations do you have? NB plus 1. How many unknowns? NB plus 1. So you have NB plus 1 unknowns, NB plus 1 equations. You can solve it, and if you solve it, you can get the solution of W's. So this gives us NB plus 1 equations, which allows us to solve for NB plus 1 unknowns. Okay, and those who have done machine learning course have already done it. It's just a repetition. There is nothing new, right? And those who have not done machine learning course, this is new for them. But yeah, so now if you do some manipulation, you can see that that psi k term that you are seeing in the top will be multiplied with y. Y will be multiplied by that psi. If I put it inside, and it will be multiplied by again the other psi's also. So we'll get that psi term, this term will ultimately be multiplied with this term, and this term. So this will get multiplied with everything. So when you get multiplied with this, you are getting something like psi I psi k multiplied by W. Okay. Here you will get psi I W naught. And now you can assume that there is a psi 0 which is equal to 1. So in that case, it becomes of the same form as this one. So W naught psi 0 multiplied by psi k, where psi 0 is 1. So then it becomes same kind of form. And here you have y multiplied by psi, right? So you can always write it in vector form. And if you write it in vector matrix form, you will get psi transpose y is equal to psi transpose psi W. This is what you will end up with. And you can come to this very easily. I did not do it, but I will do it now. In 2 lines, you can arrive at at this expression without going into this summation if you directly write things in terms of matrix vector. Okay, if I directly start with matrix vector, this is a two-line derivation. Okay, how? So using matrix vector notation, my y, and this is the vector y, this is this y, this is equal to psi, which is a matrix, times w, which is a vector, where psi, what is the form of psi? This is equal to, you will evaluate psi for each of the training samples. So it will be equal to 1, which is my psi 0, psi 1 evaluated at x1, psi, how many bases? NB, right? NB evaluated at x1. The second one will be 1, psi 1 evaluated at x2, psi NB evaluated at x2. And you can continue. The last training sample will be 1, psi 1 evaluated at x NT, psi NB evaluated at x NT. This is my psi. What is the dimension? R NT NB plus 1. This has a name. This is known as, anyone knows the name? Design matrix. This is known as the design matrix. Psi is known as the design matrix. Okay. So this is the psi that you get by using this x. That's what we did. We used this x to find out that psi. Okay. W, what is the size of W? W will be a vector of R times NB plus 1, and Y size you already know, I wrote it earlier. Now within this representation, what is my loss function? Y minus psi W transpose Y minus psi W. This will be my loss function. This will ensure that you are doing a sum of square. That's what it is doing, right? So now take derivative, see what is happening. You will directly get what I just wrote. So if taking derivative, with respect to W, so del L del W is equal to Y minus psi W, and then there will be a psi transpose coming into picture, right? And this will equate to 0, which will give you psi transpose psi W is equal to psi transpose Y, right? Correct? Straightforward, right? Because it was transpose, so it is like a square, so use the derivative law. I mean, obviously 1, 2 should come, I have not written that 2. That's okay. 1, 2 should also come, I have not written. From here, what is W? Finally, my W is equal to psi transpose psi inverse psi transpose Y. This term psi transpose psi inverse multiplied by psi transpose has a name. Anyone knows what is the name of this? This psi transpose psi whole inverse multiplied by psi transpose. It has a name. This is known as pseudo inverse. So there was Penrose, one scientist was there who came up with this actually. So this is the Penrose pseudo inverse. So if you use MATLAB or Python or whatever, you do not need to do this thing. You just use the command pinv. In MATLAB, there is a command pinv, which stands for pseudo inverse. And pseudo inverse can be applied on any matrix. It need not be square, because this psi transpose psi will make it square. You can invert it, and that allows you to do that. Okay. So this is known as pseudo inverse. Okay. And this is proposed by Penrose. So Penrose, and this has 4 properties, which I'm not discussing. If you're interested, you can read it more on the mathematical side of things. But Penrose's pseudo inverse satisfies 4 properties, but I'm not doing that. Okay, I'm not reading that. Okay, so this allows you to find out W. Okay, and once you know W, then what will you do? Your model is known. Now sample X from the PDF. Now X will be sampled from PDF. Use the Monte Carlo simulation, but instead of G, you use G hat. G hat is this model. Now, response surface method, right? This was generic. In RSM, there are 4 types of response surface method or model. The first one is type 1 RSM. What is type 1 RSM? In type 1 RSM, you write Y to be equal to beta naught, which is W naught, by the way, summation I equal to 1 to K beta I xi. A linear model, not a linear regression model, linear model in X. This is known as type 1 response surface method or response surface model. This is type 1. Okay. Then there is type 2. Type 2 is Y beta naught plus summation over I. I'm not writing the limit. Beta I xi plus summation over I, summation over j. So I, and then j greater than I, beta ij xi xj. What will happen with I greater than j? That when I is equal to 1, j will be 2, 3, 4, 5 up to k. When I is equal to 2, j will start from 3. Basically, so that the terms are not repeated. Otherwise, you will get x1, x2 and x2, x1. And we also don't want the square terms. x1 square we don't want. So that's why it's not equal to. Okay. So this is known as type 2 RSM. Type 2 RSM. Then there is type 3. And by now you have understood that these are nothing. Once you know the linear regression model that we discussed, these are all just models that you select. Nothing more, nothing less. In that case, it is beta naught plus I beta I xi plus I beta II xi square. This is basically again a quadratic model, a second order polynomial. Okay. And what do you think the last one will be? What will be the last one? Type 4. There are 4 types. There is one more. What will change in that? No. They do not go up to that much order. It will be the same order in that you think. It will be combination of type 2 and type 3. So that correlate, the combined term was missing, right? You bring that into picture in type 3, that becomes type 4. So xi, xj was missing, right? So you keep that, that is type 4. So the original response surface do not go beyond second order. Okay. So type 4. Obviously, none of these are used nowadays. but this is the basics based on which beta naught plus summation over I beta I xi plus summation over I beta II xi square plus summation over I j greater than I beta ij xi xj. Yes, yes, you can remove it and that will give you the second and third term can be, the last two terms can be combined. Okay, actually you cannot remove, it will be j greater than equal to I. Less than I still should not come because then x1 to x2 and x2 x1 will be double counted. Yeah, I mean you can do that, but the coefficients will be double counted. So that's why. So the easy thing, you are right, I can remove this term and here I can make it greater than equal to. But I am writing in this form so that you can visualize that it is nothing but combination of type 2 and type 3. So that's why I am writing, obviously. So that's all for response surface method. I think it's one of the simplest thing that you will encounter in surrogate modeling. So tomorrow I will take a lecture, but I will not do anything new. Okay, because I would have taken something new. I mean, I would have continued if I could not complete this. But since I completed response surface method, I will not take anything new. I will also not take attendance tomorrow. Okay, because day after tomorrow exams are starting, right? So, but what I will do is I will review whatever have been covered till now. Maybe give sample problems and all those things. What can be sample problems on this? Although this is not in syllabus, but I will review until this point. Syllabus is until whatever I covered on Monday. Okay, but so tomorrow there will be no attendance. But I will review everything that has been covered in this course so that you get a recap before the minors. Okay, and also I don't want to start anything new because then you will forget by the time I go to, and I have to again take that. So no point. Okay, thank you.